You know, it's pretty wild when you stop and think about it. Right now, all around us, and even through us, there are these invisible currents of energy flowing everywhere. I mean, from light that's letting you see this to the sound of my voice reaching your ears, our entire world is literally shaped by these hidden patterns, these vibrations moving through space and time. It sounds super complex, I know, but it all boils down to one simple question.
Yeah, I know. It sounds like a totally random list, right? You've got a gentle ripple in some water, a really complex sound, and then this destructive force of nature. But what if I told you that they're all playing by the exact same rule book? That they all share one single unifying identity? You guessed it, they're all waves. And really, all a wave is at its heart is just a way for energy to get from point A to point B. And they are absolutely everywhere. We're talking about the light from the sun, the sound of music, and yeah, even the powerful seismic waves that can shake the very ground under our feet.
Okay, now this is where things get really cool and surprisingly simple. Even with this huge variety of waves, we can pretty much sort every single one of them into just two main categories. And it all comes down to one thing: which way are the particles wiggling compared to the direction the energy is actually going? Let's break it down.
So, first up, we have what's called a transverse wave. Now, with this one, the vibration is at a right angle, or, perpendicular to the direction the energy is moving. The absolute best way to picture this is doing the wave at a football game, right? You stand up and you sit down, but the wave itself travels sideways around the stadium. You're not actually running from your seat. That's the transverse wave. And the second type? That's the longitudinal wave. With this one, the vibration is parallel to the direction of the energy. Think of a slinky. If you lay it on the floor and push one end, you see this little compression, this little bunching up that shoots all the way to the other end. The coils of the slinky are just moving back and forth, not up and down. So let's just put them side by side to lock it in. Transverse waves. The vibration is perpendicular to the direction. Think light, think water waves, and think of a type of earthquake wave called an S wave. Then you've got longitudinal waves where the vibration is parallel. That's your sound waves, and the other type of earthquake wave, the P wave. Simple as that. So, we've got these two fundamental types of waves. But how do we actually talk about them? How do we measure them? Well, it turns out there's this beautifully simple language that works for all of them, and it's all captured in one single elegant equation.
And here it is: V equals F times lambda. It looks almost too simple, but it is incredibly powerful. V is just the wave's speed, how fast it's traveling. F is its frequency, that's how often it's vibrating up and down or back and forth. And that weird symbol, lambda, is its wavelength, the distance from one peak to the next. The crazy thing is, if you know just two of these, you can figure out the third for any wave in the universe. It's essential for everything from how your radio works to measuring earthquakes. All right, time for the payoff. We've got the basic types, we've got the language to describe them. So now, let's use what we've learned and see how it actually helps us decode the world, bringing it all back to those first examples we talked about. Let's start with light and water. These guys are your classic transverse waves. When you see a wave moving across a pond, the actual water molecules are mostly just bobbing up and down. They aren't flowing across the pond, only the energy is. Well, light works the exact same way, just with electromagnetic fields instead of water. So what about sound? Sound is the perfect example of a longitudinal wave. My voice is basically creating vibrations that are squeezing and then unsqueezing the air particles between me and the microphone. It's a chain reaction of little pushes, just like that slinky, that carries the energy of the sound straight to you. And that brings us to earthquakes, which are so fascinating because they actually make both kinds of waves. The first ones to show up are the P waves, and P stands for primary. They're longitudinal, so they compress and stretch the rock, and they are super fast. After them, you get the S waves for secondary. These are the transverse waves, the ones that cause that violent up and down and side to side shaking. They're the ones that do most of the damage, and they always arrive second. And that's really the heart of it, isn't it? The crucial point is that by understanding just two super simple ideas, wiggling side to side versus wiggling back and forth, we get this incredibly powerful tool. It lets us understand the nature of light, sound, and even predict how these massive geological forces are going to behave. It's just a really elegant way to look at the physics of our world. So, I'll leave you with one final thought to chew on. We know that an earthquake creates fast P waves and slower, more destructive S waves. That means there's always a time gap between the first little jolt and the really dangerous shaking. So, how could you use that gap?
Well, the answer to that question is the foundation of every single earthquake early warning system on the entire planet. Pretty cool.